Dr. Vineeth Balasubramanian from IIT Hyderabad. So he is associate professor in the Department of Computer Science and Engineering at the IIT Hyderabad and was recently Fulbright Nehru visiting faculty fellow at CMU until July 2023. So today he will be speaking about causality in explainable AI. So I request him to take over. Uh, Dr. Balasubramanian, thank you for being with us here today. Over to you.
Thank you, Rucha, for the kind introduction, and thank you to you and Dr. Subhankar for inviting me for this session. So, as I mentioned just a minute ago, so I am logged in from another device. So please do feel free to ask questions. When I share my screen, I cannot see you all or see who's asking a question or if anybody types any question there. So please do feel free to interject, ask questions. I'd love for this to be interactive. I personally think I have more slides than that I can cover for sure. So I'm not interested in necessarily completing my deck. I'm very happy to keep this interactive. Stop me at any point, ask any question on anything that I cover. Okay, so as was introduced, the topic of today's session is causality in explainable AI. I'll try to give you a motivation for why we need this and also talk about some of our efforts and methods in this direction. So the TLDR, I know that everybody has very little attention span these days. So here is what is the summary of the talk is explainability is becoming an increasingly core requirement of deployed AI and machine learning systems. It's become a cornerstone of many regulations that are being brought out by different countries. But the actionable and useful explanations are the ones that are derived from causality. So how do you ensure that you integrate causal perspectives when you develop explainable AI models is the focus of this talk. Okay, so hopefully that gives you what we're going to talk about over the next, say, 45 minutes or so. Just for me to understand the time, am I correct that we have until 3? Is that correct?
Yeah.
Okay.
We'll have some time for questions before that.
Sure. Yeah. So I'll try to wrap up a few minutes before 3, so maybe we have some questions, time for discussions at the end. So just a quick primer into the kind of work that we do in our group here at IIT Hyderabad. So the thesis of our overall research directions is to learn robust, reliable systems in changing environments. And the motivation for this work is that supervised learning has, in some sense, gone from theory to application over the last decade or so. It's now more an engineering effort. If you have enough amounts of curated data, it's these days an engineering effort to make a machine learning model work on them. So then what is the next frontier of challenges that we want to work on? One is what if the supervised learning assumptions are not met, which means you have evolving environments where many things can change. The data distribution is not IID anymore. So you may have newer domains, newer classes, newer tasks. All of them constitute evolving environments. And how do you learn in a robust and reliable way in these environments is what our overall thesis is about. Very broadly speaking, we work on deep learning, machine learning, and computer vision. And our research also goes to those kinds of venues. And this overall thesis has led to 2 directions of research in our group. One is explainable and robust learning, where we focus on different aspects of explainability and learning robust deep learning models. At least one of those we'll touch upon in detail today, the causality work. The other direction is how do you learn continually in label deficient or data deficient environments, right? So this brings in continual learning, open world learning, open set learning, few shot learning, zero shot learning, generative models, so on and so forth. We've also had some interest in the theoretical understanding of deep learning models, although that's been a little peripheral at this point in time. We have a few efforts in trying to understand deep learning models from a theoretical perspective or an optimization perspective. Okay, so that's the overall outlay of the different research efforts that we have in our group. But for today, I'm going to focus on this particular thread here, which is explainability. And within that, what are our efforts towards causality in explainable AI, right? So I'd love maybe at a future time to give a talk on something other, some other topics here. But for today, the focus is going to be causality in explainable AI. So I just mentioned about a minute ago as to explainability becoming an increasing need in deployed AI/ML systems. Why is that so? I think a few years ago, about 2018, if I'm right, I think the European Union added a clause to their regulation called the GDPR, stands for General Data Protection Regulation. If any of you have worked in the industry and have worked in any adjacent areas related to machine learning, you would have definitely heard about this. And what this states is that a business using personal data for automated processing must be able to explain how the system makes decisions, right? So keep in mind, this is a law, right? So it's not something that's just stated as it is a law, which means if anybody uses machine learning to make decisions, they have to explain how they arrived at that particular decision. They cannot say the computer decided it for us. Similarly, the US has several acts. One such act is the Algorithmic Accountability Act, which talks about companies providing assessment of risks by automated decision systems. In India, we have what is called as the Responsible AI strategy that the Niti Aayog has created. There are it's out there in the public domain. If you'd like to search for it on the web and search for Responsible AI strategy by Niti Aayog, you'll actually find a couple of documents. So which even there, explainability plays a very important cornerstone of the responsible AI implementation strategy. But even more fundamentally speaking, this relates to a very fundamental right called the right to explanation. Right. So we've all heard various fundamental rights like right to education, right to public health, so on and so forth. But there is also a fundamental right to explanation. It was never invoked in the context of AI or machine learning before. It had been invoked in the context of maybe trying to understand why your credit score is of a particular kind or so on. But these days, we are talking about the right to explanation in the context of AI machine learning systems. Right. So I hope I made it clear that explainability is an increasing need. I mean, one question some of you could have is all of these European Union's acts and US Algorithmic Accountability Act is a first world problem. People like us, where we have other issues to deal about, why would we be worried about explainability in AI? That really doesn't affect us. It's not true that way, because I think we live in a very, very global world these days. So which means if a company like Infosys is developing a banking software for a bank in Germany, so if they use machine learning to decide whether a customer should get a loan in that software, so tomorrow when the customer goes and asks the bank again as to why their loan was declined, Infosys becomes responsible now because of this law, right? So which means some of these regulations directly affect us in India too. It's important to be aware. It's important to know what's happening and how do you bring explainability into AI and machine learning models. Yeah, please go ahead.
Yeah, totally. So, like, is this explanation, does it have to be in in terms that people understand, or it just has to be like a random maths? Okay, take this equation, understand on your own. Now it is explainable.
Got it. I think that's a good question. I'm just coming to that maybe in a slide or two. I'll just come to that maybe just 2 slides from now.
Okay.
So what is being done around the world? I mean, is it a new topic? What is being done around the world? There is a lot that's being done. I mean, a lot of these efforts got kickstarted by a funding opportunity that DARPA, which is the Defense Advanced Research Projects Agency in the US, they launched a funding opportunity in Explainable AI in 2015. And it's then that a lot of this work got kickstarted. And over the last 6 to 7 years, there have been many bodies of work that have been developed across sub areas of AI, be it multi-agent systems, computer vision, NLP, robotics, game theory, planning. I think in every dimension of AI, people have been trying to look at how can I explain whatever prediction or whatever the output of a given model is. Right? And if you'd like to see, there is a nice tutorial here, XAI tutorial. The link I have here is 2021 because that's the last link I could locate. But this 2021, I think they do a yearly version of this and have a fairly comprehensive view of various efforts of explainability. Okay, but that's not the focus of this talk. You can always go and look at that website if you'd like to understand this canvas of efforts. Now, coming to what Dr. Subhankar just mentioned is then what is explainability really, right? So does it mean you have to give a mathematical equation? Does it mean that you have to give a natural language explanation? And that, in my opinion, is actually the elephant in the room, right? So when people talk about explainable AI, the real elephant in the room, coincidentally, also happens to be the proverbial elephant that is felt by 5 blind people, as they say, right? So there's this popular story of how 5 blind people touched an elephant and each of them thought different things about that creature. One of them thought it was a snake by looking at the trunk. One of them thought it was a spear by looking at the tusk. One of them thought it was a fan by looking at the ear, by touching the ear rather. These are blind people. then or a tree or a rope or a wall, right? So explainability seems to be that kind of an elephant in the room, because if you consider people who are using it in practice, and by the way, explainable AI machine learning is deployed today. Many companies deploy it because they cannot deploy machine learning models without explainability based on regulations, right? So this is many of the methods that we may discuss over the course of today's talk are actually deployed in the industry today. But depending on who uses it, explainability can mean different things, right? To a business owner, it could mean, can I trust our AI decisions? To an IT ops person, it could mean, how do I monitor and debug this model? To a regulator, it may mean trying to understand whether the system decisions are fair. To a data scientist, it may mean, is this the best model that can be built? Can I improve its performance? Or to a customer support agent, it could be about, how do I answer this customer complaint? I don't want anything else, right? So explainability is a very subjective term in that sense. So maybe towards the end of the session, I'll talk about what I think is perhaps an ideal way for the community to go forward. But for the moment, I think this is a challenge at this point in time. So it depends. And if people start seeing it technically, so then there are multiple ways of interpreting explainability again. You could look at explainability as global and local. Do you want to give an explanation for every single test instance, or do you want to give a population level explanation as to saying that, okay, taking this particular taking a lot of oily food can result in a higher risk of heart disease, right? So this is a population level explanation. Do you want a population level explanation, a global one or a local one? Depends. Different situations may need different things. Do you want a model agnostic method, or do you want a model specific method? Do you want an explainability method for SVMs, or do you want an explainability method that can be added to any machine learning method that you choose to implement? Similarly, do you want something at a feature level, or do you want something at a latent concept level? Do you want something at the transparency of a model level, or do you want to reason your outcome? Right? So do you just want to understand what the neural network is doing, just so that you want to understand it's doing the same thing? Or do you want actually reason the neural network to reason out things and give you the reasons for making a decision, right? So both could be required in different situations. And there are also what are called post hoc and anti hoc or intrinsically interpretable methods, which is going to be one of the directions in which I'm going to take this talk forward. Post hoc explainability methods try to come up with methodologies that can be added as a layer on top of machine learning methods to add explanations. So which means you've already trained a random forest or an XGBoost or a neural network or an SVM, and you now want to add a layer of explainability that explains that machine learning model. Okay, this is post hoc because you add explainability after the training of the model, post hoc. Okay, the opposite of that would be anti hoc or intrinsically interpretable, where you bake explainability into the training of the model itself. Example would be decision trees. Right? Decision trees are intrinsically interpretable because the path that you take along the features gives you an idea of why you arrived at a particular decision. Right? So many different ways of looking at this becomes possible. So now going back to Dr. Subhankar's question, I don't think there is a singular way in which explainability is defined. Unfortunately, we don't have common benchmarks yet or common evaluation protocols or objective metrics yet. Every paper comes up with a different way of evaluating it. So in that sense, the field is fairly nascent in having some common objective benchmarks. And it's fair enough too, because explainability can mean different things. How I explain a particular topic to a school kid would be different from how I explain it to a college kid, right? So even for me, based on the user, I may explain two things in two different ways, right? The same thing rather in two different ways. So I personally feel that, I mean, this entire explainability should be user specific, but we'll talk about that towards the end of the session. But at this point, if you asked how should explainability be, I actually think it depends on the application. Right? So, and if you're developing a method, you need to have a particular application in mind when you develop a method and say that this kind of a method can cater to that genre of applications or that category of applications. Okay, so in our group here at IIT Hyderabad, we have been looking at multiple different perspectives to explainability. We've been working on this for the last 5-6 years, I would say. One of our earliest efforts was in post hoc explainability, a work called GradCam++, which is used around the world today. We've also been looking at intrinsic interpretable or anti hoc explainable methods. So we've been looking at both kinds of methods over the last few years. But one of the things we've been more closely looking at is trying to separate these explainability methods in terms of causality, which one of them use causal principles in coming up with explanations, and which kind of methods don't use causal principles. And we've been working on both too. More recently, we've been looking at papers that look at causal principles to develop explainable models. Right? So this is just a sampler of different efforts we've had over the last few years. And obviously, as the title says, I'm going to focus on the causal ones in this talk. But just to very quickly introduce a couple of our efforts which are non-causal. This was a work called GradCam++, published in WACPI of 2018, where we introduced a very simple pixel level weighting strategy for while computing gradients for explanations. We in fact show that it could come up with a closed form solution for those pixel level weights. And this work has been available on arXiv and GitHub for the last few years. And what is gratifying as an academic is that this method is used around the world for different applications. It was extensively used during COVID to actually explain machine learning models' decisions on chest X-rays. It's also being used in solar array panel defect understanding, or in healthcare in different applications, or even in agriculture. Okay, the work has more than, I think, as we speak, more than 1,800 citations. And it's gratifying as an academic when you see a method actually translate to practical use. More recently, as I said, we've also been looking at building anti-hoc explainability. This is again non-causal. I'm just introducing you to a couple of quick efforts before I go into the causal side. So this work was published at CVPR last year, where what we tried to do was take any existing deep neural network. How do you make it automatically explainable by design? Right? So intrinsically, how do you make it explainable rather than add a layer of explainability? And the way we go about doing it is through this simple idea, where we say that if you have a backbone network that attends to an image, then you have your standard output, the last layer here, and then you say, give the output as say this being a cheetah. Now what we do is we have a bypass layer here, which goes into a set of concepts, and these concepts help reconstruct the image and also try to predict the same outcome. Why is this useful? Now, these concepts can maintain some semantics. So the first concept here could be the texture of the skin. The second concept here could be the color of the animal. The third concept here is the number of legs it has. The fourth concept here could be is whether it has a tail or not, so on and so forth. Right? So these are different concepts that you have. Why is that helpful? Now, when I implement a method this particular way, I can look at an image and say it's a cheetah by saying that it's a cheetah because it has spotted skin, it has 4 legs, it has a tail, and it is yellow in color or golden in color, and so on and so forth. So not only am I saying it's a cheetah, but I can now rationalize my decision as to why it is a cheetah. Right? And we show that this kind of an approach can work with supervision for concepts, without supervision for concepts, so on and so forth. If you're interested, the paper is again available on arXiv. It was a CVPR 2022 paper. So these were some of our efforts in trying to build explainability into deep learning models. But what I'm going to focus on, say the rest of, say about half hour or so, is why causal. Right? So life seems so simpler. I mean, in the last couple of slides, I gave you a couple of examples of how explainability could be built in. Isn't that enough? Why complicate our lives by bringing causality? And how do you go about it? Okay, so that's what we'll talk about now. So the first thing is to introduce you to what is causality or what is causation itself. Right? So here is a very simple statistical example. There are many such online, but there's just one example that I picked up. So where if you see the statistics of say ice cream sales and shark attacks, okay, you will see that both of them peak during summer. Right? So you have more ice cream sales in summer. You also have more shark attacks in summer. Okay, that's when the sharks come. A lot of people go swimming and sharks come and probably grab them. So now if it happens that these two variables were inside a data set and one of them, let's say, was an input variable and one of them is an output variable, the model is going to think and predict that whenever ice cream sales increases, there is likely to be a shark attack. Right? So that's what machine learning does. Right? So that's what machine learning models do. They try to establish build on the correlations that exist between your different variables. But we know that this is not causal by any means. Eating ice cream is not going to increase your risk for a shark attack, right? But that's what you would get from such an isolated data set. So the question then is, how do we separate such correlations from causations while coming up with explainable models. Okay, I'll also take another perspective to this, maybe a couple of different perspectives to motivate this work. Right, so let's take an example that's closer to what we've all seen over the last few years. Let's take COVID. Okay, so there's a very popular paradigm in causality called Simpson's paradox. So let me actually explain that to you. So let's assume that during the COVID pandemic, there were two vaccines that were floating around. Right? So let's say they were called vaccine A and vaccine B. And depending on a person's condition, which could have been mild or severe, the outcome of the person or the mortality of taking the vaccine was a person could end up alive or dead. Okay, these were the different options possible when you took that vaccine. Now let's assume that let's go back to a time when you were yet to take your vaccine, right? We all know the panic we were all going through at that point in time. Let's say a news article or somebody shared this information with you. It's the mortality rate table, right? It says that vaccine A has 16% mortality. That is, among all the people who took that vaccine, only 16% passed away. But vaccine B had 19% mortality. Right? Among the people who took it, 19% passed away. Now, if I asked any of you, now you have to choose a vaccine, right? So you're going next day to take your vaccine, but you have to choose between one of these. And these are the mortality rates that have been released publicly. Now, which vaccine would you pick? Any thoughts? Would you choose A or would you choose B? You can speak or you can just type your message. What would you pick, A or B?
So it depends on the data set. Like if like
this
the
is all is given
you,
to you. This is all is given to you. Imagine the newspaper published only this much. I mean, consider the real scenario, right? You have to take a vaccine, and this is what was shared with you. Now, and these are sometimes often the kind of data that's shared with us too in practice. Which one would you pick?
most probably the 15%, like which has less mortality
It's
rate.
practical, absolutely, right? Even I would do that, right? So because the mortality rate is lesser with A, makes sense, and that's what you should pick and go with that vaccine. Okay? Now let's delve into one more level of detail. Let's say that somebody, some insider of some organization gave you a little bit more of detail, and they said, you know what, they published only this data, but the actual data is this. Okay? This data states that vaccine A, if you look at the last column here, that's the same as the previous one. 16% mortality is for A and 19% mortality for B. But when you divide it by mild patients and severe patients, that is, you look at the condition of the patient before they were administered the vaccine, you notice that in both of those cases, B actually had lower mortality. In both those cases, not just one. In both those cases, B had lower mortality. Okay, if you don't believe me, you can look at the numbers here. Okay, all those numbers add up. Now, with this inside information, which treatment will you pick? Any thoughts? Okay. B, right? Because it seemed even for mild condition patients, it had lower mortality, and severe condition patients, it had lower mortality. Now, the bigger question is, then how did it even happen that A got the lower mortality if B had lower mortality on both these cases? How do you answer it? Any thoughts? I think the answer is on the screen, but any thoughts on how do you answer that? Okay, the answer is in the numbers. You see that more number of people with severe conditions were actually given B vaccine. And with severe conditions, the overall mortality will always be high. And because of that bias of more severe condition patients going to vaccine B, B ended up having a higher overall mortality rate, although it had a lower mortality rate both in mild and severe conditions. This seems like a paradox, right? If you look at the overall numbers, A has the higher, lower mortality, but you look at each condition, B has the lower mortality for each of them. So this is known as the Simpson's paradox. If you search online, you'll find several examples of doing this. This is just a COVID way of presenting it, but there's several other examples that you may be able to see. Now, if we asked you which treatment to choose, you could say B, but the answer is it still depends. What does it depend on? It depends on what is called as the causal graph. If the condition was impactful in the treatment and the outcome, you should go for treatment B. But if the treatment itself resulted in the condition, which resulted in the outcome, treatment A may still be okay. Right? So the causal graph, or how was the actual data created or generated, if you can get an understanding of that, you can make more wise decisions in these kinds of scenarios. Okay, hopefully this should have given you a little bit of motivation as to why thinking of something from a causal perspective makes sense, right? Because plain statistics can sometimes be misleading. Okay, that was one example. Let's come to machine learning and talk about why causality in machine learning, right? So I'm quite sure all of you know that the core objective in supervised machine learning is that X and Y, we want to model how X data and Y labels are related. Okay, that's the core objective of supervised machine learning. Now let's see an interesting scenario. Let's consider two random variables X and Y, okay, data and labels. Let's just assume there are three kinds of ways in which the variables could be related. X could have caused Y could have caused X, or there could have been a third variable that caused both X and Y. Okay, three possibilities here. Now, based on the first possibility, I write what are called as structural equations. Okay, these are called structural equations in causality. So I just write a relationship. I just say X is a random number and Y is a function of X. I write out that function. Similarly, I write one for the second causal graph and I write one for the third causal graph, and I find that all three joint distributions are exactly the same. Okay, now this is interesting because when you're given a training data set, what you see is only these. So you see one of these joint distributions in your training data set, but the problem is it could have been generated by any of these three now. So what is the true causal model that generated this data? You don't have access to. The first question you may ask me is, why do I have to worry? If I can fit the data perfectly and predict, why should I worry about what data created, what process or what causal generative process created this? Okay. This becomes important because it only fits this data perfectly. Whatever model you come up with will only fit this data properly. The moment you want to now generalize to newer domains, newer tasks, then trying to build a model on just the data is going to fail when you have newer data coming from one of these three causal models. In first causal model, newer data will get generated differently. In the second causal model, the newer data will get generated differently, and so on in the third model. So let's see this in practice. So if you now went ahead and changed something in the first model, you now see that the distributions start changing. So if you start changing a variable, in all of these cases, you set X to 3, but now change something else, you now start seeing the distributions to be changing. So although your training distributions were the same, when at test time, if you probably set data to come from a new domain or a new task or something like that, things are now going to start looking different. And what you built as a model for one distribution may not work for all the three causal graphs. So knowing the true causal relationships is essential if you want to build robust models. Otherwise, you'll be building models based on only correlation. Okay, so now let's go one more level before I start talking about a few methods. Is why does it matter in explainability? And okay, I see that causality makes some sense, but why does it matter in explainability? Okay, let's take an example. Let's assume now the typical way explainability is implemented today. I said that explainable models are deployed today. So the typical way they are done using some methods is that if you have a neural network that predicts the risk of heart disease, let's say, and you've trained a model, deployed it, and it's possible that you use one of the post hoc explanation methods and it picks one of the variables, let's say high blood pressure, as the explanation for the high risk of heart disease. I mean, that's one way of explaining a model, is to see which feature was responsible for a particular outcome. Because telling that to the user, if somebody came and told me that my risk of heart disease is high, the first thing I would ask is why, what is that variable, so that I can work on it. Right? If they come back and tell me blood pressure, well and good, right? So that's good. But the problem is this may just simply be a correlation. Everybody who comes to a hospital with the risk of heart disease, or probably even just comes to the hospital, is likely to have a high blood pressure. Now, saying that that is the cause for the risk of heart disease may not be appropriate. It's possible that there was some other confounding variable, let's say body mass index, which caused both high blood pressure and risk of heart disease. Now, telling a patient that their body mass index is the reason for risk of heart disease is more important than saying blood pressure, because that's what they know. That's when they know what to really address to causally solve the problem. Okay, and this is the motivation for bringing causal principles in explainability. I mean, I can give you multiple examples, but one more. There are many companies where they are trying to implement machine learning in aerospace settings, right? So, for example, in an aircraft, to do autopilot for a certain distance in a long haul flight or something like that, they use machine learning, right? In case there's at some point in time, let's say there is some flaw, some snag that happens, and there's a particular reason that's given as to why that's a flaw, or what that explanation that's given for a particular prediction the model is making, right? If that explanation is not causal, it's going to be a big problem, because an aircraft can have thousands of sensors, and if there is one problem, at least 20 different sensors can go wrong. Now, it's most useful to an aerospace person if they know which one of those sensors was causally responsible for the outcome, rather than all the other sensors that went kaput just because of correlations, right? So there's a reason why causality becomes useful in these kinds of scenarios, especially risk-sensitive scenarios. Okay, and that's the reason why we study causality in explainable AI. More generally speaking, causality studies higher levels of abstractions of reasoning called intervention and counterfactuals. I'll probably skip that in the interest of time. But supervised learning looks at just one level of reasoning called association, which is P of y given x, right? I hope you all agree with me that supervised learning essentially tries to solve the estimation of the conditional probability P of y given x, which is supervised learning. But there could be higher levels of reasoning, which causality typically studies, such as interventions and counterfactuals and so on and so forth. Now I know I have about 15 to 18 minutes. So now I'll talk about a few of our methods, and many of the methods that we come up with are all first principle methods, which means we were perhaps the first to do whatever was done. Nobody else had done that at the time of our doing. So I'm going to probably talk at least about a couple of our methods very briefly, and always happy to take questions towards the end. So what I'm going to talk about is how do we then bring causality into explainable AI, and how do we get such causal explanations? So one of the first works that I'm going to talk about is a work called Causal Attributions in Neural Networks, published in ICML 2019, a few years ago, joint work with students Aditya, Piyushi, and Anirban. So when we did it, this was one of the first causal efforts for attribution in neural networks. By attribution, what we mean is which feature attributed towards the outcome. Okay, that's what you can call as an explanation or a reason also. Okay, that's what we call as attribution. So what we try to see here is, if you have a trained neural network model, right? So this is a post hoc approach, by the way. I'll talk about the anti-hoc approach or the intrinsically interpretable approach a little later. So if you have an already trained neural network, I want to find out what kind of causal relationships did that neural network learn. That's the essence of this particular problem that we try to solve. And we want to isolate the causal relationships that it learned from other kinds of correlational relationships that it may have learned. Okay, to do that, you first of all need to understand what is the fundamental framework of causality. Causality starts with what is called as a structural causal model, out of which any data gets generated. Right? So we see data all around us, and all of the data got generated in some form. Right? That generative model is typically represented as a structural causal model, which contains a few endogenous variables, which are your observed variables, a few exogenous variables, which could be noise and random environmental parameters, F, which are the causal functions that connect different endogenous variables in your system, and finally a distribution for your noise variables or an exogenous variable. Okay, this is what is set to define a causal model. If we knew this, machine learning is not required. Okay, because we exactly know the causal functions of how one variable caused another variable, and if we know the exact equations, then machine learning itself is not required. Right? You can straight use that model to make predictions. So this is an example of a structural causal model, where if you have a causal graph such as this, the equations that connect each of those variables in this graph is typically called a structural causal model. So the first thing that we do in our work is to look at a neural network as a structural causal model by itself. Right? If we assume that we want to study the relationship between input and output variables, we can marginalize over all your hidden variables. You can also keep them if you want to reason on them, but typically we reason between input and output variables. So then we marginalize all the hidden layers, and we reduce the neural network to a graph such as this, where the input variables A, B, C, D, E, F are directly connected to the output variables J, K, L. And we do accept and acknowledge that there could be some unknown variables like U1, U2, U3, U4, which we call as exogenous variables, which we don't know, they are latent, but we know that they could affect the creation of these variables A, B, C, D, E, F. What are we acknowledging there? We are acknowledging that A and B may not be independent. Both of them may be jointly caused by some other variable called U1, just that we don't know it, right? Because the data set gives us only A, B, C, D, E, F. But this is what we refer to as the structural causal model. So this is the way we define this reduced structural causal model after marginalizing your hidden neurons as M prime. Okay, L1 is your layer, first layer of the neural network. Ln is the last layer of the neural network. So what we try to do is to compute something called the causal effect between the input and output variable inside a neural network. I'm going to slightly go faster because we may not get time to cover all the details in depth, but happy to stay back at the end if you want to answer if you have some questions. So for continuous variables, we define the causal effect or the average causal effect, as you can see denoted by ACE, as expectation of y given do xi equal to alpha minus a baseline xi of the same value. So here you may have not come across this thing called do. Do stands for a notation. It's in fact a calculus of a calculus. It's called the do calculus that's used for understanding causal relationships or between variables. So this simply means that what is the expected value of y given that I intervene on a variable xi, that's one of the features of your input x, and set it to alpha minus expectation of y given that I set xi to some baseline value. Right? Just to give you an example, if I have to find out how causally responsible blood pressure was towards an increased risk of heart disease, I have to see if I set the blood pressure to 160, how does the outcome of different people of risk of heart disease change when compared to the blood pressure being 120. So if that also would have an expectation. So if I do that, I would get an average causal effect. Okay, this is a first principles definition of average causal effect. So we realize that this is what we want to compute for a trained neural network. Okay, existing attribution methods don't do such causal analysis. They don't implement this do notation. They may use, say, gradients to get the relationship between an input and an output variable. So how do we compute this ACE is one of the objectives of this particular paper that we came up with. And the way we go about doing it is to divide this ACE into two parts. The first part is called an interventional expectation, which is given by an integral, which we don't know how to compute for a neural network. The second is the baseline, which while I gave you a baseline for blood pressure, that may not work for all kinds of problems. How do you solve it for other kinds of problems also becomes a challenge to do. So the rest of the paper in our work, which I'm not going to go into detail, is about how do you compute these two quantities. Right? How do you compute this expectation term? It's also called the interventional expectation because you intervene on a variable and set it to alpha. And the expectation is typically called an interventional expectation, and it's given by this integral. How do you compute that? So we come up with using a Taylor series expansion and then maximizing it, and then using the notion of separation between input neurons to simplify it to a form which can actually be computed. In fact, the interesting conclusion that we make here is that this interventional expectation here that we need to compute can be computed in terms of observational means and variances of your input data. Remember, the observational means and variances of your input data can be pre-computed. If you give me a training data set for each variable there, I can compute the mean and variance and keep it even without training a machine learning model. Right? So we show that you could actually get the interventional expectation directly from observational means and covariances using some mathematical jugglery that we do in the paper. Right? So the other thing that we also study in this work is it only for feed-forward neural networks? Not necessarily. We show that you can also do it for more complex architectures, such as recurrent neural networks, because there you have the same variables coming at each time point. And how do you study the causal effect of a particular variable at a particular time on the output is what we show can also be done by this particular framework. So in our results, we show that the average causal values that we get actually match independently obtained values equivalently. And we also have an interesting real world case study where we study this approach on anomaly prediction in an aircraft dataset. Where in an aircraft dataset, we try to predict whether the aircraft would have a bad landing or a good landing. and we try to isolate which features were responsible for a bad landing in the case of bad landing. And we actually show that the way our method identified those causal features actually matched the FDR report or the flight data recorder report for the flights in practice. We also got this validated by aircraft engineers at Honeywell to find whether the causal explanations that we got actually made sense in practice. Okay, and it actually happened to do. So if you're interested more in this work, I'm not going to go into very gory details here, but if you're more interested, you can look at the paper. It's available on archive, or the code is also available on GitHub if you're interested. Yes, yeah, please do go ahead and ask.
Yeah, sorry. So this causal model that you're learning, it's still based on the data set that you have, right? It's still dependent on the data set as much as possible, right?
Sure. So as I mentioned, this particular work, we only do, you've already trained a neural network on a particular data set. Absolutely, yes. The only thing we're trying to study in this work is what kind of causal relationships did the neural network learn? I mean, please keep in mind that a neural network learns whatever it has to learn to solve a problem, which means it may have learned some correlational relationships, it may have learned some causal relationships, right? Because it just does whatever it needs to solve that problem. So we want to isolate the causal relationships and the correlational relationships within a trained neural network, right? So just to quickly answer the question in a more broader way, I'm going to, in the next few slides, talk about the reverse part of it, which is this side angle to this. If we had access to prior causal domain knowledge, how do we integrate them while training neural network models is the complement of it, which I'll talk about in a moment. So, but what we had here, you're absolutely right. It's based on a trained neural network model, which was trained on a particular data set. But what we're just trying to isolate is what kind of it was causal relationships and what aspect of it was correlation. Did I answer that question?
Yes. I remember like the public health and all those experiments are, very much this kind of driven, right? So specifically causal, right? So they very focus is fixed. They look at intervention, they look at control sets, and then they define the entire study. They collect very few features and the goal is fixed. And probably your next paper probably targets to others. Maybe I'm wrong. But
actually it does. Maybe
okay.
Since you brought that up, let me actually explain that using that example. So the next work was in ICML last year. I think the actual title of the paper was Matching Learned Causal Effects, but overall what we propose is causal regularization with domain priors. Once again, to the best of our knowledge, it was a first principles work, not done before. I'll quickly talk about what we try to do here. So in the earlier work, what we tried to do was we took a trained neural network model and see what kind of causal relationship did it learn, right? Now we know how to quantify the causal relationships inside a neural network. Now the question we try to ask is, if I had access to true causal knowledge, right, domain knowledge, as like how you mentioned, typically the way this is studied in clinical studies and in many other domains, econometrics too, is people conduct what are called clinical trials and run it over many years and then get some knowledge of relationships between different variables. For example, there could be an organization that conducted a clinical trial over 10 years and concluded that if you take paracetamol, right, all of you probably take paracetamol when you have a fever. Let's say they could have shown a causal relationship saying that it helps to a certain extent and after a certain point it can deteriorate the health. Right, so they may have an inverse U-shaped relationship between the taking a paracetamol and the effect on the person's health. Right, so there could be different such clinical studies. Now we all are moving towards a data-rich world. Right, I'm quite sure you've heard of many hospitals collecting data and building machine learning models, which can be deployed so that you can predict many aspects of a patient's health. Now in data-driven models, all the knowledge that the doctors have gained over the last few decades is completely tossed out the window, right? Because you're just taking a new data set and building a new model. Whatever clinical trials was done in the past, you are assuming that the model will learn from that data, which may not be true. So what we try to do here is, if you have some prior causal knowledge, right, only for partial variables, not for the entire data set, you may only have some knowledge about one particular input variable and output variable, and you have a data set from which you want to train a machine learning model. Now, how do I ensure that this neural network model that I train on the data set respects that causal relationship that I already know? Is what we try to do in this work. That's what I hope that answered that question too. So we look at our work as actually a way of implementing those kinds of clinical studies and clinical trials and bring it into data-driven models like machine learning models or deep learning models. I know I only have a few minutes. I'll very quickly try to summarize this. So this is what we try to do. We assume that we have some domain priors that we know from a given domain. For example, it may be very, very simple domain priors, right? So for example, I know if I'm going to build a machine learning model to predict college admissions, I know that increasing your GATE score or JE score or SAT score is going to improve your chances of college admissions. I know that relationship is monotonic. I may not know the exact shape, but I know it's monotonic, right? So that information is enough for us, right? We say that means the neural network, when it learns a machine learning model to make a prediction, it should respect the fact that that particular score should be monotonic, right? That's what we try to do in our particular work. We call this causal regularization. I won't go into the gory math again here. We show that we can control 3 kinds of causal effect in our work: controlled direct causal effect, natural direct causal effect, and total causal effect. Okay. This is just one example of a definition of a controlled direct effect. So there are different ways of defining causal effect when you get into the nitty-gritties. We show that you can do it on 3 kinds of causal effect in this work. And one important thing that we show, which is also an important topic in causality, is the notion of what is called identifiability. Identifiability in causal literature means the condition that permits us to measure causal relationships using observed data. If I give you a data set, how can you identify whether the relationship between 2 variables in your data set is causal or correlational? In general, that's a non-trivial problem. But under certain conditions, if the graph was a tree-like structure, or if the graph had a particular structure, under certain conditions, it is possible to say that given a data set, I can identify what direction of causality lies between one variable and the other variable. And that notion is called identifiability. So we show that for a neural network, we can identify effects such as controlled direct effect, natural direct effect, and total causal effect. And we come up with a regularization procedure to actually implement this. I won't go into the details, but just show you our overall algorithm, which is very, very simple, where we show that when you train a neural network, in addition to whatever loss term you add, you simply add also one regularization term, which ensures where the regularization is between G and M effectively. G is the causal domain prior that you were given, and M is the gradient or the Jacobian of the neural network. You want to match the Jacobian of the neural network with the gradient of the domain prior that you were given. Very simple. But we show that this much is enough to provably maintain that. This is what we prove here. We actually prove that that much is enough to provably maintain a causal effect inside a neural network. Okay, so if you just did this matching, we are guaranteed to maintain. We said that we want to maintain a certain monotonic causal effect inside a neural network when you train it, because we knew it from the past, right? We should leverage that rather than simply rely on a data set, right? So that's what we do in our work, and we show this kind of an approach can be used for maintaining monotonicity, maintaining fairness, right? I may say that a particular variable should have 0 effect on an output. Let's say I have a machine learning model to predict whether a customer should be given a loan or not. I may want gender to have 0 effect on this outcome. If you use ERM, that's your standard loss functions in machine learning, you get a green curve, right? So this is a particular data set where if you intervene on race, the effect on recidivism, or you can look at some criminal charge or criminal suspicion or something like that, goes up as you change the race. We ideally don't want this to happen by race. You ideally want this line to be 0, that as you change the race of a person, you don't want it to impact recidivism, whether the person will become a criminal or not, right? We show that using our approach, we're able to take it closer to the red as compared to the green, right? So you can see in some of these cases that we are far more closer to the red than the green itself. Not only this, we show that you can also do this with different kinds of shapes. If your causal domain prior was W shape, we can maintain it. If your causal domain prior was J shape, we can maintain it. If your causal domain prior was U shape, we can maintain it. Not just 0 causal effect, not just monotonic causal effect. Whatever causal effect was known from prior domain knowledge, we can maintain it as causal knowledge in the neural network also. Okay, once again, if you're more interested in this, The paper is publicly available and you can look at it in more detail later. Okay, I know I've run out of time. I had just to quickly walk over. We also have some work on how do you go beyond direct effects? How do you also model indirect effects, right? Remember, the moment you have a neural network, those neural networks are not, input variables are not connected. You're assuming independence between input variables. And we all know that real world data is not necessarily independent between the input variables. Now, in those scenarios, how do you handle indirect effect? Right? One input variable could affect another input variable, which may effectively affect the output variable. Now, how do you model this is also something that we've been doing. I won't go into it now. We've also been looking at trying to use causal perspectives to mitigate bias in image classifiers. We've also been looking at how do you use this to generate better counterfactuals and disentangle representations from a causal perspective. In the interest of time, I'll skip these. Just to quickly conclude with some open problems and challenges in the space. While there has been a lot of work in explainability over the last few years, many fundamental problems continue to remain. One of the problems is there a universal formalization for explainability itself? Remains an open problem. It's been noticed that the moment you focus on explainability, your accuracy starts falling down. So how do you balance accuracy and explainability or interpretability? How do you maintain both of them becomes an important question to ask. How do you evaluate explainable systems, right? I mentioned earlier that this entire space is still subjective. How do you evaluate explainable systems? And if you use post hoc methods, where you add an explainable method as a layer on top of a machine learning method, who owns the explanation? If something went wrong, was it because your explanation methodology was wrong, or was it because your model learned wrong relationships between input and output? How do you decide that remains an open task. The moment people start suing people, these kind of things will become important, which is, I think, around the corner. And more generally speaking, from an AI perspective, AI has historically always seen two branches, connectionist AI and symbolic AI. Symbolic AI works on logic. Connectionist AI is more neural network-ish. I think this is a good opportunity for these two to come together to solve problems on explainability and come up with logical explanations. Going back to one last point, I said I'll come back to this towards the end, is how do you then go about explainability? I think it's the way to go about it, in my opinion, is to allow more porosity between users and machine learning models. Currently, you have machine learning models that are learned, deployed, and users just get the predictions and work with it. I think we have to start treating machine learning models more like software, where the first step is user requirement specification. We know that in software development, there's an entire life cycle model, different kinds of models like the waterfall model, where you start with user requirement specification. I think we need to move towards machine learning models which start with user requirement specification, where for a given application, a user can say that I want prediction, but I also want a natural language explanation. Right? Or I want a prediction, I don't want a natural language explanation, I just want transparency. Right? A user specifies what they want, and we accordingly build machine learning models as we move forward. I feel that that's perhaps the solution to doing explainable AI. Otherwise, it will continue to remain a very subjective and qualitative way of looking at this space. With that, I'll stop. Just thanks to all my students, collaborators who have kindly been involved in all of this work, and also to all our funding sponsors who have kindly supported our work over the years. Okay, I'll stop here. I'll be happy to stay behind for questions. Sorry, I went a bit over time. I hope it gives some perspective to this topic in terms of both the motivation and methods. Thank you again for attending.
Thank you, sir, for the wonderful talk. But I have one question. Like, as you have talked about grad chem plus and like how you use it to calculate the gradient of the pixels and then calculating the whole heat map kind of thing.